So, we're already on the 9th and penultimate lecture of our series. So today we're going to talk about 4 advanced topics in C++, which are closely linked to program structure. The idea of static data, function and class templates, which is a very efficient way to write functions that have the same structure for multiple classes, the use of namespaces, and probably most importantly, the use of header and multiple source files. So, without further ado, let's start with the first case, static class members. The idea is that an object is an instance of a class. Right, essentially, you've all seen it. Each object has a unique set of values for its data members. There's nothing shared between different objects. So an object may also not exist forever, right? It may be destroyed when you exit a function, when it goes out of scope. It's inside a curly bracket loop. So all that stuff could make a difference. Sometimes we may want all objects from a given class to share access to and be able to modify some specific common data, which is usually called global data between quotes. And the way to do that is to create a static data members. A static data members really means the memory for that given data member is reserved for the lifetime of the program, and it can also be accessed by all objects. So there's only one of these static data members, not as many as we have objects. So let me show you how to implement one. Here I've got a class, my class, which has two members, an integer x and a static integer which is called nObjects. We then fiddle with it, so the constructor and parameterized constructor both increment the number of objects, and the destructor decrements the number of objects. And I've got a show function which prints out x and the number of objects, and we'll see what happens in a minute. Then I call that a few times. I've got a function called test which does it internally. So the reason to do this is this goes out of scope, and so the A3 gets destroyed. So it would be really interesting to see what happens. So if we do int main, I declare a1, a1.show, a2, a2.show, I call test, and then I call once more a1.show just to see what happens. So let me explain a little bit more what happens. So we had this static int and objects. The other one that was really important, that inside the code, outside the class, I made this statement, I initialized the n objects. That's really important. If you define a static data member, it has to be done outside the class. Every object is instantiated from our class, can see the same n objects and modify it. In our example, we use it to contain the current number of objects which are changed in both the constructor and destructor. And no big surprise, the code outputs x equals 1, 1, x equals 2, 2, x equals 3, 3, which was A3. A3 goes out of scope. If I then process A1 again, there's only 2 elements left of it, so essentially n object is 2. So that's quite an intriguing way of doing it. So, next topic, templates. And in the first instance, function templates, which are the easier one. Templates allow functions and classes to be created for a generic data type, without telling you what a data type is. So we consider functions first, and let's look at an example we looked at before, the function double maxval or int maxval, which takes a double or an integer as an argument and returns a if a greater than b and b if a is not greater than b. So we used overloading to write the function for integer parameters. The second function performs an identical task to the first, maximum of 2 numbers, but with a different data type. And we use the ternary operator, this thing with the question mark in there, test question mark if true colon if false, which is very good for true or false test. It also returns an L value, not an R value, as you might expect. So there's also weird and wonderful stuff you can do with this. Okay. Overloading is good but laborious because you need to write a function for every type. So I want to write a single function which is called a template. So a template tells me what the argument is. In this case, it's a class I call C-type, and I've got a function that returns a C-type and takes two C-types as arguments, and what it does is the body of the function is the same as what we've seen before. Now I can declare a double x1 and a double x2, and I can actually call the function maxval square sharp bracket double sharp bracket x1 x2, and I also can call maxval integer I1 I2, where these are integers, and what you get the right function for those two cases. So we only had one definition, but we can make many functions out of that. That's quite a powerful piece of technology. The function template started clearly with the statement that it was a template. It had a class argument. Again, the angle brackets are used over there, and the rest goes through normal. The angle bracket statement tells the compiler the template is for a generic type C-type, which is known as the template parameter. The remainder is like a function, except the data type is replaced by C-type. The compiler will not use the function template until an instance is created. And that's what I did. If I call the function maxval double, that's an instant of the template. So, and there may be many instances of the template in a generic code. So, I said I can do it with functions. I can also do it with classes. So let me show you how it works. So suppose I have a function pair of numbers, class pair of numbers, which has two private integer arguments, and it can add and subtract them, and then I can do stuff with that. And that's lovely. I've got a pair of integers, but suppose I want a pair of doubles. Well, it's slightly annoying because I need to copy that whole code again, and my code grows and grows and grows and grows, which is clearly not where I want to be. So how do I deal with that? So what I really do is I change the code as follows. I declare a template, but now it's a class template, so it's a class pair of numbers which has this template argument C-type, and everything internally to it which needs to be a C-type is now declared as C-type. The way I use this is almost the same thing as before. I've got a pair of numbers with square bracket argument int IP, which I initialize to x and y, and I can have a pair of numbers double dp, and then I can call exactly the same function on these objects. So that's a very efficient way of doing things. Class and functions. And the statement I did, right, I had a template for the class, the pair of numbers has now the new arguments, and instances were created by these two functions. Again, the compiler used the class template to create two instances, or template classes, one for each type as required. And you've seen this already, because you use vector double, and vector int, and vector float, which are all, a vector is actually a class template, and vector double creates a template class for vectors of doubles. Okay, so there was nothing new about this. You've been using it without knowing it. If a member function contains a parameter that's an instance of a template class, it must refer to its type as with the correct type. The compiler, so with toNum, will replace C-type with int, double, etc. as appropriate when creating a class. For example, if you write a simple copy constructor, toNum const toNum C-type n dn, and it does that kind of thing over there, that's perfectly fine. That is a copy constructor, but you can see inside that thing we again need to, so this is a toNum, but you need to refer to the C-type over there, not over there, interestingly enough. For member functions defined out of the class, we prototype inside the class as before, and then outside the class you really need to define the function as a function template. So if you declare it outside the class, you have to put a template in there. Inside you don't, but you have to work explicitly in this way. And you must also modify the class name before toNum, because you need to tell it what class it's part of. So things get a little bit complicated if you do it that way. And there's a type over there that should have read C-type, which is what I changed everywhere. Okay, so that's perfectly correct. Must also modify the class as referring to the template class. Now, something simple, namespaces. Imagine if we try to include two classes with the same name, both called myClass, and in this case they're pretty similar, but apart from the fact myClass, first one contains one integer, the other contains two integers. And clearly if you compile this code, you get a compilation error. The reason is that you have what is called a name collision, in this case a class name collision. you've got the same thing meaning two different things. That can't happen. That's not good. Okay, so there clearly is a solution for that. It's called a namespace. So if you wrap around each of these classes a namespace, which is different, namespace my underscore ns1, namespace my underscore ns2, not the best variable names ever, but it works. It shows me what I'm doing over there, and you can clearly see what happens over there, and that works all perfectly fine. The reason is a namespace is like a container, a box. It allows us to keep class definitions distinct, right? They're in separate boxes, and we can choose which one to use. You can implement namespaces in two ways. The first is direct reference to the namespace using the scope resolution operator, as you've done over and over again for the standard class. So my underscore namespace, my class, will get the one in namespace 1, and this will get the one in namespace 2. So that's perfectly fine, and that's how things work. So I feel reasonably happy about that part of it. The second method is maybe appropriate when you only use one namespace, which sometimes happens. So for example, I can put inside a function using namespace my namespace 1. There's no risk of confusion. There's only one namespace I'm using, and then my class will be the one in namespace 1. In this case, I could still refer to the my namespace 1 class directly, and the my class within my namespace is not used. We're already very familiar with the namespace standard to an extent. That namespace contains all the standard library, although we use the first method above when I use namespace my underscore namespace 1. The final part of today's lecture, which is actually a really important message, is the use of headers and multiple files. So when your code grows large, you must, and I emphasize, must divide the code across files for readability. First thing to consider is where to put constants, class definition, and function declarations. The normal place is in what is called a header file. We include the contents of header files as follows, right? IOStream, CMath are system header files. A personal header file is put in between double quotes. It's usually called .h or in some systems .hpp, whichever choice you make. It's not as standard. Note the difference between those system headers and your own headers, and you can include this header in every CPP file that makes up our program. Header files are for class definition and function declaration. Where should we put the function definitions? That's a very good question. I'll discuss that next. Function definitions, what functions actually do, usually go in a CPP file. Function definitions, whatever functions actually do, usually go in a CPP file, especially when substantial. We can create a second .cpp file to hold these. Example, you could put the function definition for show in a separate file, which would be called myclass.cpp. You would now have three files, myclass.h, myclass.cpp, and myproject.cpp. We name files as appropriate, but the house style requires the same name for the header and the implementation. So myclass.h, myclass.cpp. Keep all these files in your projects folder. Now, there is potentially an issue with header files. Definitions can be made only once. If the functions in the CPP file are okay, what I mean, if the implementation CPP file, you include the header file in there, it's only included once. But headers containing class definitions may be automatically included more than once. You include them in other headers, and that really means that you get confused. There's a very neat technique to do that, which is called a header guard, to prevent this multiple definition issue. And the best way to do that is, unfortunately, with preprocessor directives. It's not the most elegant way, but it perfectly works. See the header file myclass.h for an example, and what I see over there, I say if def, which means if undefined. If that thing is not defined, then I define it. And there's an end if over there, so this if, and that end if matches, so this only gets executed if myclass.h is undefined, and then it does this declaration. If I include it a second time, myclass.h is defined, and it won't read all of that code again. So that's smart trick to use, which is so common that essentially I have to tell you that. And then you can include this thing in there, because you can include myclass.cpp over myclass.h in multiple files as well, and there are really no issues at all with doing all of this. Everything works. So there's a small issue with that. In case of a template, things don't work exactly that way. Using the method for splitting code in multiple files discussed above, with a .h and a .cpp file with the same name, can cause serious errors when using templates. And the reason for that is that template classes and functions are not really defined until they are generated because your code asks for them. There's a consequence is that the compiler needs to see both the declaration and the definition in the same file as the code that uses the template. So the default rule above was that there are no function definitions inside a header file. You are expected to break this rule for templates. The solution is essentially, I'll show you what happens over there. Okay, essentially if you look over here, you can clearly see I've got a template class over here, and all of the function definitions, which are done in here in this case, are declared. They're all within this header guard, and that really means that when this code uses that file, it all works the way we expect it to. So it's quite subtle. You need to be specific about the relationship between a template class and friends, and this is particularly important also with the insertion operator. I can't even write, operator, and here's how to do it. So before the class definition, you add something like that, right? It's a template class C-type my class, template class C-type, and what I do is you can already see that I have a rather complicated operator structure over there, and in the body of the class, you declare a friend as follows. Okay, so the weird thing is this gets done before the class, and this gets after the class, and finally you declare the operator itself, and that requires the class namespace. Right? That's why there's a my namespace operator in there. So there's quite a subtle piece of code, and I would suggest you study the example I put in the code directory for this week. So to summarize, we have covered the idea of static class members, function and class templates, namespaces, header and multiple source files, and the pitfalls and additional issues we have to face when we work with templates. Thank you very much.